Okay, today we're going to do optimization problems, which means you're going to be trying to find the maximum of something or the minimum of something. Okay, we're going to do four practice problems together. So let's look at this one. It says, a man has 100 feet of fencing, a large yard, and a small dog. He wants to create a rectangular enclosure for his dog with the fencing that provides the maximal area. What dimensions provide the maximal area? Okay, so here's what we're going to do. We have a picture right there, but let's make it just a little bit simpler. Also, let's look at this. Okay, all right. I guess we'll make it like that. Okay, so we have y here and x here. That's exactly the picture that's given to us. We're just looking straight down at it. Okay, so we're talking about how much area he can enclose with 100 feet of fencing. Okay, what is the area? The area is length times width, right? So that's going to be x times y. And we want to maximize that. So we want to find the maximum of x times y. Okay? Now, there's two variables there. You see, I can write area equals x times y. And I could say find the maximum of the area. So we would try to find the derivative of area and set it equal to 0, just like you did on the test for finding the maximum of a function. Okay, but here's the one problem. There's two variables, x and y. So how are we going to get around that? So here's what we're going to do. There's two other sides of the rectangle that aren't marked yet, right? Let's mark those. This up here would be x, and this would be y. So, how much fencing is needed? Well, there's two sides of length x and two sides of length y, right? The amount of fencing needed is x plus y plus x plus y. That's how much fencing is being used. And how much fencing do we have? We have 100 feet. So we want that to equal 100. Okay? So that means 2x plus 2y is going to equal 100. Which means 2y is going to equal 100 minus 2x. Which means that y is going to equal 50 minus x. So now, when I do area, and I write area equals x times y, I can replace the y with 50 minus x. So I get area equals 50x minus x squared. You see, that's only a function of one variable now. The only variable is x. I can even write a of x. Starting right there, I can, because there's no more y. There's only x's. Okay, so now the problem is very straightforward. They just want us to maximize this. They want us to maximize the area. How do you find the maximum of something? You find the maximum by calculating the derivative. What's the derivative of the area? It's going to be 50 minus 2x, and then we set the derivative equal to 0 to find critical points. Remember that? And solve for x. So we'll get 50 equals 2x. So 25 equals x. That's the only possible area. That's the only possible answer that I can find, right? So that must be the answer. But let's check something. What did I just do? I just found the critical number, right? And like I said just a second ago, I only found one critical number, so I suppose that must be the answer. But in general, if somebody asks you to maximize something or minimize, you start off by finding the critical numbers, right? There sometimes might be more than one. So how can you be sure which one gives you the maximum? You use the second derivative test, right? So here I kind of don't need to do that because there's only one possible answer, so that must be the right answer. But I think it's a good idea to check and make sure that that will give us the maximum area and not the minimum area. Okay, so I would take an extra 30 seconds to plug 25 into the second derivative. So what would a double prime be? Look, it'd just be -2, right? Which is less than 0. So the graph would be concave down, which tells me that this is going to give me a maximum. So the maximum area is for x to be 25. 25 what? 25 feet. If x is 25 feet, how long should y be? Remember, y is 50 minus x. So if x is 25 feet, then so is y. And there's the answer to our question. The man in the problem should make a square yard, 25 feet on all 4 sides. And then that will provide the maximum area inside the fence for his dog to run around. Okay? Notice the question said, what dimensions provide the maximum area? And we just answered that question. If the question said, what is the maximal area? Then after finding out the shape, I would now calculate the area, which would be 25 times 25, which is 625 square feet. But I'm not going to do that because they didn't ask. They just said find the dimensions. Okay? Let's do the next question. It's almost the same, except... Just 1 second, please. The only difference here is there's a little river or a stream on one side of the property there. So the person only needs to build a yard with 3 sides of fencing. Okay, so let's read this problem. A woman has 100 feet of fencing, a small dog, and a large yard that contains a stream that is mostly straight. She wants to create a rectangular enclosure with maximal area that uses the stream as one side. What dimensions provide the maximal area? Okay, so this is almost the same problem. Oops, wrong color there. Okay, let me try that again. There we go. Okay, now the only difference is that this time there's a little river running right here. My computer's really not working very well today. Okay, that's the river. All right, so Okay, I think it's done. Okay, so all we have to do this time is build fencing on this side, and this side, and this side. Okay, so this time the only difference is instead of x plus y plus x plus y equals 100, this time we only have y plus x plus y equals 100. So 2y plus x is 100, which means 2y is 100 minus x, which means that y is 50 minus 1/2 x. Okay? So now when I calculate the area is x times y, because it's a rectangle. So we have area equals x times y, and y is 50 minus 1/2 x, so the area equals x times 50 minus 1/2 x. The only variable there is x, so I'm going to write a of x. And if you prefer, you can write that like this: 50x minus 1/2 x squared. We want to maximize the area, so we find a critical number or numbers. There might be more than one. Let's find out. We take the derivative. A prime equals 50 minus what? X, right? We set that equal to 0. Solve for x, and we get 50 equals x. Now I'm going to do the second derivative. Is what? -1, which is less than 0, which means the function's concave down, which means this gives me a maximum. So I just found out that this length should be 50 feet. What is y? Y is 50 minus half of x. So that's going to be 50 minus 25, which will be 25 feet. And there's our answer to the question. She should make it so that the distance across here is 50 feet, and the distance going back this way is 25 feet. Don't worry about the fact that in the picture, the 50 feet looks shorter than the 25 feet. That's because we didn't know yet at the time which was going to be the longer side. So I just drew the rectangle that way. Okay. I could easily, if somebody complained about that not looking right, I could easily say it's not drawn to scale. Okay, let's do the next problem. This one is a little bit different. Let's see what it says. A power line needs to be run from a power station, which is right here, located on the beach, to an offshore facility, right there out in the ocean. Okay? It says figure 4.5 shows the distances between the power station to the facility. Well, it doesn't show the distance actually between the power station and the facility, which is this distance. That's not what it shows in the picture. But it does show us that you go 5,000 feet down the beach and then 1,000 feet out into the ocean. That will get you from the power station to the facility. Okay? All right, now it says it costs $50 per foot to run a power line along the land and $130 per foot to run the power line underwater. How much of the power line should be run along the land to minimize the overall cost? Okay, so this one's a little bit harder. So what they're saying is that this stuff right here that you run along the land costs $50 per foot. And this stuff that they run underwater costs $130 per foot. And they want to spend the least amount of money. So what they're asking is how much should they go down the beach before they turn and start going underwater? That's what they're asking. Okay? The two extremes are this. You might have one person say, well, it's so much cheaper to run the power line on the land than it is in the water, so why don't we do this? Why don't we go all the way down the beach and then turn and go straight out? That's one suggestion, right? Let's see how much that would cost. That would cost them 5,000 feet times $50 per foot plus 1,000 feet times $130 per foot so what would that be? That would be 75, no, that's not right, sorry, 25, and then 4 zeros. So that's $250,000 to go down the beach, plus a 13 and 4 zeros. That's $130,000 to go out to sea. So that would be a total of $380,000. Okay, that's one possibility. That's one extreme possibility. Somebody else now might come along and say, no, that's a dumb idea, because that's the longest distance. This person might say, I know my geometry, and I know that the shortest distance between 2 points is a straight line, so we should do this. Just go straight out, because that would be the shortest possible distance, so it must be the cheapest. Okay, let's see if that person's right. Let's calculate that distance real quick. I'm going to use the Pythagorean Theorem. I'm trying to find that distance out there. Okay, we know how to do that. We know that 5,000 squared plus 1,000 squared should equal question mark squared, right? Well, that's actually 5,000 feet if you want to write feet in there. Okay, so that's going to be $25 million plus 1 million equals question mark squared. And if we add those together, that's 26 million. So question mark must be the square root of 26 million. Okay, let's calculate that. So that's about, I'm going to round off to the nearest foot. That's about 5,099 feet. Okay, so this person who's coming along and saying this is much shorter, so let's do it like that. Okay, let's see how much that would cost. So when this person comes along, we're now going to do 5,099 feet times, well, that would all be underwater, right? So that would be times $130 per foot. Okay, 5,099 times 130. And that ends up equaling $662,870. So look at that. That's surprising. That costs almost twice as much as this, even though it's a much shorter distance. So that's a little bit surprising, isn't it? Now, the smartest person in the room steps up and says, you guys are both wrong. The best thing to do if we want to save money is to go down the shore a certain distance, and again, the question is, we'll have to decide where should the turn happen in order to come up with the minimum cost. Okay, so here's what we're going to do. We need to decide how far we're going to go along the shore, and then when we make the turn, how long will that be? We need to find those two things. Okay, so here's what we're going to do. Let's use this triangle to help us here. You see that triangle right there? Let's use that to help us. So we'll call this side right here X. Let me make that black so it stands out more so we can see it. We're going to call that X, feet. Okay, we already know this side is 1,000. So that means that this distance right here would have to be the square root of x squared plus 1,000 squared, right? What am I using there? I'm using the Pythagorean Theorem. X squared plus 1,000 squared under a square root. That's the distance of the wiring that's going to go from the beach out to the station or whatever that is out there. And how much wiring is going to be lying along the beach? Well, that's going to be 5,000 minus x, right? Okay. So now we have that situation, and let's calculate the cost. This will be pretty straightforward. The cost equals, there's this much on the beach, that many feet, and it costs $50 per foot. So we multiply that times 50. Plus, we have some wire running under the water. How much? This much. Let's see, what's 1,000 squared? That's 1,000,000, right? So that much is running underwater, and it costs $130 per foot, so we multiply that times 130, and there's our cost. The only variable is x, so let's write c of x. Okay? And one other thing I'm going to do, that square root, I'm going to write that as an exponent, okay? Because that makes it easier when you're doing the derivative. Okay, so we want to minimize the cost. So we find critical numbers, which means calculate the derivative. So do you agree that the derivative will be 50 times negative 1 plus, and then let's be careful here, we're going to have 130 times 1/2 x squared plus 1,000,000 to the power negative 1/2 times 2x. So what we have here is we have negative 50 plus 130x over the square root of x squared plus 1,000,000. That's our derivative. How do we find critical numbers? We set the derivative equal to 0 and solve for x. So I'm going to set the derivative equal to 0. Okay. Let's move the 50 to the other side. And what would you like to do next? How about if we say 130x will equal 50 times the square root of x squared plus 1,000,000? Does that make sense? Now I think at this point the easiest thing to do might be for us to square both sides to cancel out the square root. So let's square both sides. On the left, we're going to get 130 squared, which is 16,900, x squared, and then equals, and on the right, we're going to get 2,500 times x squared plus 1,000,000. Okay, distribute the 2,500. These numbers are kind of large, but the algebra that I'm doing should be straightforward for you. This is just basic algebra. Okay, subtract 2,500x from both sides. We will have we will have 14,400 x squared equals a 25 followed by 8 zeros. So x squared equals this number divided by this number so x would be the square root of that, which is going to be 50,000 on top, 120 on the bottom, and of course we can reduce that. That would be 5,000 over 12, and I can even reduce that further. That actually comes out to be, let's write it as a mixed number, 416 2/3. Okay, so that's what x equals. Now, a couple of things. Number one, remember, x was this distance right there in the picture up there. Okay, so let's write that in. 416 2/3 feet, which would be 416 feet and 8 inches. Okay, something else. We need to actually find these numbers. Okay, that's number one. But number two, before I even spend time on that, I need to make sure that this will minimize the cost and not maximize the cost. How do you do that? You calculate the second derivative. Okay, I'm going to explain it verbally. We're not going to write it all down. Okay, but you would calculate the second derivative. So that means the derivative of this, okay? Plug in this number, and what you're going to find is you're going to find that you get a positive answer, which means the graph is concave up, which means this gives you a minimum, okay? But you might choose to not even do that, because you might say, like we did in the first two, found out, well, I only got one critical value, and so that critical value must be the answer I'm looking for, because if it's not, then what would the answer otherwise be? Okay? But if you wanted to really check it, that's what you would do. Okay? So, let me ask you a question. What is that number right there? That would be 5,000 minus 416 2/3 feet. So that is 4,583 1/3. Okay, and how much is this distance right here? Well, you just take your x and plug it in. Okay, that comes out to be about 1,083. Okay, I'm rounding off a little bit there. But let's go ahead and put in the exact answer, which would be an extra 1/3. So let's not round that off. In the book they round it off, but I'm being a little bit more careful here, and I'm not rounding off. Okay? So there's our measurements. It says, look back at the question. It says, How much of the power line should be run along the land to minimize the overall cost? So that answer is right here. 4,583 feet and an extra 1/3 of a foot, which is 4 inches. Okay, there's another question. It says, what is the minimal cost? All right, we still need to answer that, so let's go ahead and answer that right now. Let's find the cost. It's going to be easy to find the cost. All I have to do is take the amount on the beach and multiply that times 50. It's $50 per foot. And then take the amount underwater and multiply that times 130, and then just see what we get. And that comes out to exactly $370,000. And that's the minimal cost possible. Okay, we're going to do one more problem together, and then we'll stop. This one's a much shorter question. Let's see if it'll be shorter to answer. It says, design a closed cylindrical can of volume 8 feet cubed, so that's 8 cubic feet, so that it uses the least amount of material. In other words, minimize the surface area of the can. Okay, remember that the volume of a cylinder, if you did not remember this, you could just look up what's the volume of a cylinder. Okay, it is pi r squared h. That's the volume, okay? And we are told that the volume of this can is 8. So here, let's do this. Let's just put an 8 there instead of the letter V. Okay, 8 cubic feet. All right, they want us to minimize the surface area. The surface area of a cylinder is 2 pi r squared plus 2 pi r h. Again, if you did not know that, all you would have to do is look it up. Okay? And we want to minimize that area. So we'll set the derivative equal to 0 and do all that stuff, okay? So one problem here, like the first two examples, we have two variables, r, but also the variable h. So how do we get around that problem? We're going to use this. Because pi r squared h equals 8, then that tells me that h must be 8 divided by pi r squared. So in my formula for area, I can replace the h. Whoops, that should be a plus sign. I can replace the h with 8 over pi r squared. And then you see that we get some canceling, right? The pi's cancel, and we get some canceling on the r's, and we're actually going to just end up with 16 over r. Correct? So that's a formula for the area. The only variable is r, so I will write A of r equals that, and I want to minimize, so I calculate the derivative. Okay, now a prime of r would equal 4 pi r. That part's very easy, right? Plus, now this part you need to be a little bit more careful about. What's the derivative of 16 over r? Think about that. It's 16 times r to the negative 1. So when you do the derivative, you're going to get negative 1 times 16r to the negative 2, right? So in other words, we're going to get minus 16 over r squared. Okay? That is a prime. Now I want to minimize the area, so I want to find the critical values of area. So I set the derivative equal to 0. So we have 4 pi r minus 16 over r squared equals 0. And let's solve that for r. We'll get 4 pi r equals 16 over r squared. 4 pi r cubed equals 16 over 4 pi. Sorry, not yet, just 16. Then we divide by 4 pi. And we get r cubed equals 16 over 4 pi, which is, of course, 4 over pi. And so now we finally have r. r is the cubed root of 4 over pi. Okay, there's your radius. Hold on a second. Okay, there's our radius. The cube root of 4 over pi. Now we need to find the height. Okay, so remember, pi r squared 8, h equals 8. So that means that h equals 8 over pi r squared. And we just calculated r, so let's plug that in. 8 over pi times r squared. And so that's what the height of the can should be. 8 over pi times the cubed root of 4 over pi squared. And just for the sake of having an idea of how big those numbers actually are, the radius there, if you plug that into a calculator, that's about 1.08 feet. And the height comes out to be about 2.17 feet. Okay, so that's what the cylinder should look like.